Thank you, Daisy and Zach, for the wonderful discussion on the theoretical basis of Darcy-Brinkman flow. Given the solutions previously mentioned, we ask ourselves the question: how does changing various parameters within these equations actually affect the pressure and velocity distributions? Well, dear viewers, that is exactly what I'm here to discuss with you. The first topic we're going to tackle is how does a change in porosity affect the velocity and pressure distributions. I would like to direct your attentions to the following graphs here that depict the velocity components in the axial and normal directions versus the channel height at constant x position, separation coefficient lambda, and membrane filtration coefficient. When considering the axial velocity distribution, we can see the general trend we've seen before in the 1D Brinkman solution. It reaches its peak at the center between two plates, the furthest point from the effects of the boundaries. The normal velocity component, however, increases from 0 at the channel center to its maximum value at the boundary wall due to the suction velocity boundary condition. As we begin to increase our porosity parameter, and therefore decrease our overall porosity, our velocity profiles dampen. The effects of the decreased porosity are, however, more dominant in the normal direction compared to the axial. Please keep in mind that since the effects of porosity are dominant in the normal direction, it also has a dominant effect on filtration. If we take a look at the pressure distribution here, we can see that as the porosity decreases, our maximum magnitude of pressure increases. If we take this one step further and begin to increase the membrane filtration coefficient instead, thereby increasing the membrane's ability to let fluid pass through, the normal velocity distribution steepens, as seen in the graph. As we all know, while it is important to consider the velocity and pressure distributions, we also need to consider our derived variables: axial flow rate, leakage flux, and mean pressure. Before I do so, however, I would like to define two important characteristics for flows in permeable membranes: reverse leakage and reverse flow. Reverse leakage occurs when the mean normal velocity is negative, which means you have flow back into your channel, thereby contaminating clean fluid with fluid within the channel. The streamline pattern here, not related to the paper results, illustrates an example of this phenomenon. Reverse flow, however, is when the mean axial velocity is negative. This streamline pattern example, also not related to the paper results, illustrates this very well. What we see here is a reverse flow along the channel length, with a strong flow through the permeable channel walls. And indeed, this phenomenon is seen in the streamlined solutions presented in this paper as well. By increasing the dimensionless filtration coefficient, or the inlet pressure, a reverse flow is introduced, which helps the filtration of the fluid. Coming back to our derived variables, I would like to highlight the equation for the axial flow rate, Q, here. We see that the ratio between the axial flow rate and the inlet flow rate is equated to a right-hand side dependent on the separation parameter, the channel height, and the dimensionless number eta. Our dimensionless eta term, as we recall from Zach's report, is proportionally dependent on the inlet pressure and inversely dependent on our porosity parameter. The axial flow rate, as it turns out, is strongly influenced by this eta. I would like to direct your attention now to this figure comparing the axial flow rates along the channel length with different values of eta. For any value of 1 or greater, the flow rate decreases exponentially along the channel length, eventually reaching a region of reverse flow once the axial flow rate becomes negative. The greater the value of eta beyond 1, the sooner the flow reverses. And indeed, this was seen in the streamline graphs, when the value of the inlet pressure was increased, and thereby increasing the value of eta. and a region of reverse flow appeared within the channel. I would also like to highlight the concept of leakage flux described by the equation here. Within this equation, we can see that the leakage flux also has a dependence on the same parameters as the axial flow rate and shares its strong dependence on the dimensionless eta number. The current figure illustrates that with increasing eta, increasing leakage is also seen. The last equation I would like to go over with you all is the mean value of the pressure difference shown here. From this equation, we can see that the mean pressure is also dependent on the separation constant, the channel height, and the dimensionless eta. While for all eta values there is an initial decrease in the mean pressure along the length of the channel, for higher values of eta we see a reversal and an increased mean pressure, which indicates an area of reverse flow within the channel, which is favorable to the ability to filter. Now on to Colin, who will discuss the fascinating ways these results can be applied.